Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to close your eyes for a second. Imagine you are floating in the absolute crushing darkness of the outer solar system. You are maybe 1 billion kilometers away from the sun. It is colder than any winter you have ever experienced.
Yeah.
Colder than the Antarctic plateau in the dead of night. And looming in front of you is a giant polished snowball.
It really is one of the most hauntingly beautiful objects we've ever discovered. You're talking about Enceladus, Saturn's 6th largest moon?
Exactly. From a distance, if you were just flying by, it would look dead. It looks like a frozen statue, perfectly white, reflecting almost all the sunlight that hits it. A silent, icy rock.
And that was the assumption for a very, very long time, that it was just another ice ball. But as we got closer, that assumption, well, it shattered.
Literally shattered. Because when you look at the southern pole of this moon, the ice isn't smooth at all. It's cracked open. It looks like a broken eggshell. And from those fractures, which are massive, by the way, they're called tiger stripes, these incredible geysers are erupting. Giant plumes of water vapor and ice are just shooting out into the vacuum of space at hundreds of miles per hour.
It's a dynamic, almost violent process. It's actually spewing out so much material that it forms one of Saturn's rings.
The E-ring.
The E-ring, exactly. So this isn't a dead world, not by a long shot. It's a world that is actively bleeding its insides into space.
And that visual, that bleeding ice, it hides this massive mystery. We know there is a liquid ocean beneath that shell. We know, thanks to missions we'll talk about in a minute, that this ocean is spitting out organic material. But the core question, the one that I imagine keeps astrobiologists staring at their ceilings at 3 a.m, is about the history of that material.
Provenance is everything in this field. It really is. It's the difference between finding, say, a fossil and finding a fresh footprint in the mud. The question is this material fresh? Is there chemistry happening down there right now, actively cooking up the building blocks of life? Or is Enceladus just a deep freeze? Is it a celestial storage locker that's preserving ancient dust and chemicals that have been trapped in the ice since the solar system formed 4 billion years ago?
That is the billion-dollar question. Is it a kitchen or is it a museum?
That is a perfect way to frame it. I'm going to borrow that. If it's ancient dust, it's a fascinating history lesson about the early solar system, no question. But if it's active chemistry, if the kitchen is open for business, then it's a potential habitat.
Well, buckle up, because we might finally have a lead. And the crazy thing is, this clue didn't come from a spaceship. It came from a lab right here on Earth.
Yeah.
Just yesterday, January 18th, 2026, a breakthrough study was published in the journal Icarus. A team led by Max Craddock at the Institute of Science Tokyo, working with researchers across Japan and Germany, decided that since they couldn't go back to Enceladus right now, they would bring Enceladus to them.
They essentially built a moon in a bottle. It's an amazing piece of work. They didn't just look at old telescope data. They built a physical, chemical model of that subsurface ocean. They wanted to see if they could actually synthesize the ingredients of life under those specific, very alien conditions.
So that is our mission for this discussion. We're going to unpack this incredible experiment. We're going to look at how you recreate an alien ocean in a laboratory, what exactly they found swimming around in their test tubes, and why this specific study brings us one step closer to answering that huge question: are we alone?
It really is a fascinating story of forensic science on a planetary scale. It's like a CSI investigation, but the crime scene is 1 billion kilometers away.
Okay, but before we get to the new science, I think we need to set the stage. We really need to talk about what we knew before yesterday, because we didn't just guess that Enceladus was interesting. We had a scout out there for a long time.
We did. We absolutely have to talk about the legacy of NASA's Cassini probe. It's impossible to overstate how much that mission changed our understanding of the outer solar system.
Cassini was the spacecraft that changed everything.
It really was. Cassini arrived at Saturn in 2004, and it stayed there until its grand finale in 2017, a 13-year mission. Before Cassini, if you asked an astronomer about Enceladus, they would have shrugged. It was just a small, bright moon, one of many.
A dot of light.
A dot of light. But Cassini provided what we call ground truth. It didn't just orbit at a safe distance, it got daring. It actually flew directly through those plumes we mentioned.
I still can't get over the audacity of that maneuver. Flying a multi-billion-dollar robot through the geyser of an alien moon. It feels like something out of a movie.
Oh, it was incredibly risky navigation. The mission planners were probably sweating bullets, but the payoff was huge. And remember, it also flew through Saturn's E-ring. That ring isn't made of rocks or big chunks of ice. It's largely made up of the fine ice particles that Enceladus has been ejecting for eons.
So Cassini was literally flying through the exhaust of the moon.
That's it, exactly. It was sampling the moon's breath.
And it wasn't just taking sightseeing photos, it was tasting the spray.
Right. Cassini was equipped with some very sophisticated noses. Technically, we're talking about mass spectrometers and an ultraviolet imaging spectrograph.
Okay, let's pause there for a second. Mass spectrometer is one of those terms that gets thrown around a lot in science news. For the person listening who hasn't been in a chemistry lab since high school, what is that instrument actually doing?
Think of it like a very, very precise coin sorter. Or maybe a toll booth for molecules. You take a sample of gas or dust, the stuff from the plume, and you give it an electric charge. Then you shoot it through a magnetic field.
Okay.
Lighter things get deflected a lot by the magnet. Heavier things, they just plow straight ahead. By measuring how much each particle bends, you can calculate its mass with incredible precision. And if you know the mass of a molecule, you can usually identify what it is.
So you see a particle that weighs 18 atomic units?
That's water. H2O. You
Yep.
see one that weighs 44. That's carbon dioxide, 2 UO2s. It's a way of taking an inventory of the chemical zoo.
So Cassini is flying through this plume at thousands of miles an hour, catching these tiny particles, and instantly weighing them to see what the snow is made of.
Precisely. And what it detected was, well, it was shocking. We expected water ice, maybe some simple salt, some dust. But Cassini found a diverse array of organic compounds.
Now, we have to be really careful with the word organic here. When a chemist says organic, they are not talking about pesticide-free kale at the grocery store.
No, definitely not. That's a common point of confusion. In chemistry, organic is a very broad term. It just means molecules that are based on carbon. Carbon is the backbone. Cassini found simple stuff like carbon dioxide and methane, but it also found larger, more complex hydrocarbon chains.
Okay, so why does that matter? Why did finding hydrocarbon chains make everyone in the planetary science community just lose their minds?
Because on Earth, those chains are the scaffolding. They're the absolute precursors to biology. You cannot have life as we know it. You can't have proteins, you can't have cell membranes or DNA without first having these carbon chains. Finding that spewing out of a tiny frozen moon meant that Enceladus wasn't just a dead ball of ice, it was chemically active. It had the potential to be a factory.
It just captures the imagination. You see those readings, carbon, hydrogen, nitrogen, and you immediately jump to life.
It's a natural leap to make, a very exciting one, but that is exactly where we hit the scientific gap. And this is the gap that Max Craddock and his team really zeroed in on in this new paper. Cassini was amazing at telling us what was there. It was like shouting from a distance, "Hey, I found some interesting building materials over here."
Right.
But it was completely silent on how they got there.
That brings us back to the origin debate we touched on at the top, the kitchen versus the museum.
Right. The debate really split into two main camps. Camp one is active hydrothermal synthesis. It's a mouthful, but the idea is simple. This theory says the chemistry is being produced inside the moon right now. Imagine hydrothermal vents at the bottom of Earth's oceans, these hot, mineral-rich chimneys, cooking things up like a pressure cooker. The idea is that Enceladus has the same thing going on.
And Camp 2.
Camp 2 is the primordial or inherited theory. This suggests that the organics are ancient. They are essentially cometary dust. This is the stuff that was floating around in the nebula that formed the solar system billions of years ago. It got trapped in the ice when the moon formed, and now it's just passively leaking out.
So Camp 1 implies a living, breathing engine. Camp 2 implies a dusty, ancient storage locker. Why couldn't we just figure this out in the lab before now? I mean, why did it take until 2026 to really tackle this?
Well, we tried. People have been doing origin of life experiments for decades, but honestly, I think we were looking at the wrong map. Previous laboratory studies were almost always focused on conditions relevant to the early Earth, trying to figure out how life started here. Or they looked at the chemistry of deep space comets and interstellar clouds. They rarely focused on the specific, unique, and frankly punishing environment of Enceladus.
It's like trying to learn how to bake a cake by studying a grilled steak. You might learn something about heat and food, but you aren't going to figure out how to make a souffle.
That's a really fair analogy. Max Craddock's insight was simple but profound. We need to stop looking at generic space chemistry and start looking at Enceladus chemistry. They needed to build a bridge between the known laws of chemistry and those specific, spiky spectral readings that Cassini sent back all those years ago. They had to prove that the moon's specific environment could, in fact, create these molecules from scratch.
So let's talk about how they did that. This is the part that I found really fascinating. How do you build a moon in a bottle?
You start with the ingredients. The team created a chemical mixture based strictly on what Cassini actually observed in the plumes. This is critical. They didn't add anything extra just to make the reaction work. They stuck to the recipe provided by the moon itself.
I looked at this ingredients list, and I have to say, it does not sound very appetizing. We're talking about things like ammonia and hydrogen cyanide.
Definitely not a cocktail you'd want to drink.
Hydrogen cyanide.
Yeah.
Isn't that famously toxic? Like spy movie suicide pill topic?
Yes. Absolutely lethal. It shuts down our ability to use oxygen at a cellular level. But in the context of prebiotic chemistry, the chemistry that comes before life cyanide is an absolute superstar. It is a vital raw material for building bigger things.
Okay, make sense for me. How is a poison a superstar?
It's all about reactivity. Cyanide is a carbon atom triple bonded to a nitrogen atom. That triple bond stores a lot of energy. It's unstable in a way that makes it want to react with other things. If you want to build complex organic molecules, you need Lego bricks that like to snap together. Cyanide is a very, very sticky brick. A lot of theories about the origin of life on Earth also rely on it.
Okay, so they have their toxic soup. That's the recipe. Now they need the oven.
Right. And for that, they used a high-pressure reactor. Specifically, the paper calls it an autoclave pressure chamber apparatus.
An autoclave? That's basically a high-tech industrial Instant Pot, isn't it?
Essentially, yes. That's a great way to think about it. It allows them to subject that chemical mixture to immense pressure. We have to remember, this ocean is buried under kilometers of thick ice. The pressure down there is crushing. If you just did this experiment in a glass beaker on a lab bench at standard atmospheric pressure, you wouldn't be simulating the moon, you'd just be making a mess.
But Enceladus isn't just a static pressure cooker, is it? It's not just sitting there. It's moving. It's in orbit.
It is, and this is the key variable that so many previous studies often missed. Enceladus is in a slightly eccentric orbit around Saturn.
Eccentric meaning oval-shaped, not a perfect circle.
Exactly. It's not a perfect circle. That means that sometimes Enceladus is a little bit closer to Saturn and sometimes it's a little bit further away. When it's close, Saturn's massive gravity pulls on it harder. When it's far, the pull is weaker.
So the moon is constantly being squeezed and released, like someone squeezing a stress ball.
Yes. This is called tidal forcing or tidal flexing. This constant squeezing and stretching creates friction deep inside the moon's rocky core. That friction creates heat, and that heat is what keeps the ocean liquid. If that orbit were a perfect circle, Enceladus would likely be a solid block of ice to the core.
So the orbit is the heartbeat of the moon. It's the engine that drives the heat.
Correct. But it also drives a cycle of circulation. The water gets heated near the core, it rises up through the ocean, it cools down near the ice shell, and then it sinks again. Or in some cases, it gets pushed up into cracks and fissures in the ice and freezes, and then maybe melts again later. It's a very dynamic system.
And the researchers actually simulated this cycle. They didn't just turn the heat on and walk away.
They did. And this is the truly brilliant part of the experimental design. They didn't just heat the mixture up and let it sit there. They subjected it to repeated cycles of heating and cryogenic freezing.
Heating and freezing, back and forth, back and forth.
Exactly. The heating phase mimics the hydrothermal activity, the water circulating near those hot core vents. The freezing phase mimics the water's journey up through the cold ocean, or perhaps its passage into the icy shell itself. It captures the dynamic movement of the fluid within the moon.
So they aren't just testing, does heat make molecules? They are testing, does the life cycle of the moon's ocean make molecules?
Yes, that's a much better way to put it. The theory they were testing is that the heating triggers the initial reactions. It breaks down the simple stuff like that ammonia and cyanide. And then the cooling and freezing phases might stabilize or further process those reaction products. It's a rhythmic chemical process driven by the orbit of the moon itself.
That is incredibly cool. It's like the moon is breathing and every breath cooks the chemistry a little bit more.
That's a beautiful way to put it, a perfect analogy.
So they ran these cycles. They took their primordial soup, they squeezed it, they froze it, they heated it, and they squeezed it again. Let's get to the payoff. What happened in the reactor?
The experiment worked. And it worked almost exactly as predicted, which in science is always a moment of immense relief and excitement. These artificial hydrothermal reactions didn't just produce some brown, useless sludge. They produced a really wide array of complex organic molecules.
We're talking about things significantly more complex than the ammonia and cyanide they started with.
Oh, much more complex. They created aldehydes, they created nitriles, and perhaps most significantly for the search for life, they created amino acids.
Amino acids. Okay, that's the headline for me. Even I know that one. Those are the building blocks of proteins.
They are the fundamental alphabet of life as we know it. You, me, the bacteria on your skin, the plants outside, we are all built out of proteins, which are just long folded strings of amino acids. Finding that you can make them from scratch in a bottle using only the ingredients present on Enceladus under Enceladus-like conditions, that is a very big deal.
And here is where it gets really, really interesting for me. You mentioned the freezing cycle earlier. I think most people, myself included, assume that freezing just stops things. You put food in the freezer to stop it from changing, to stop chemistry. But you're saying something different happened here.
This was one of the most surprising and, I think, critical findings of the entire study. You're right. Usually cold slows chemistry down, molecules move slower, they bumped into each other less often. But in this specific case, the researchers found that the freezing process wasn't just a pause button. It actually helped to generate simple amino acids, specifically glycine.
Wait. The freezing helped make the glycine. How does freezing something make a reaction happen faster or more efficiently? That seems counterintuitive.
It does, doesn't it? It's a phenomenon called the concentration effect, or sometimes you'll hear it called eutectic freezing. Think about what happens when salt water starts to freeze. The ice crystals that form are pure water. They push the salt and everything else dissolved in the water out.
Okay, so the ice is pure, and the liquid that's left over gets saltier and saltier.
Exactly. As the ice forms, the remaining liquid gets pushed into these tiny little channels and pockets between the ice crystals. In those tiny channels, the concentration of your chemicals, your cyanide, your ammonia, your aldehydes skyrockets. They are jammed together in a very, very tight space.
Ah, I see. So even though it's cold and the molecules are moving slowly, they're forced so close together that they can't help but react with each other.
Precisely. The growing ice acts like a vice, squeezing the reactants together and forcing them to interact. So the icy shell of Enceladus isn't just a barrier or a lid. It might be an active participant in the synthesis of life's ingredients, a chemical factory in its own right.
That completely changes how I picture it. I always thought of the hydrothermal heat as the life giver and the ice as the death bringer. But you're saying the cycle needs both.
You need the fire and the ice. The heat provides the energy to break the initial bonds. The ice provides the concentration to force the new bonds to form. It's a two-step process.
That's almost poetic. Now, creating these things is one thing. But remember, the whole goal was to match Cassini's original data. So they took these lab products and they analyzed them. But they didn't just use any standard lab equipment, did they? They were very clever about this.
No, they were. This is where the real forensic part comes in. They analyzed their sample using a laser-based mass spectrometer that was designed specifically to mimic the instrument on Cassini. The instrument on the spacecraft was called the Cosmic Dust Analyzer, or CDA. They essentially built a lab version of that.
Why go to that trouble? Why not just use the best, most modern, highest resolution machine you have in the lab in 2026?
Because you have to see the data through Cassini's eyes. Cassini's instruments are, incredible feats of engineering, but they're based on technology from the 1990s. They have certain limitations, certain quirks, certain resolution in how they display the data. If the researchers used a modern 2026 super scanner, they might see things Cassini missed or see them differently. By mimicking the Cosmic Dust Analyzer, they could make a direct apples-to-apples comparison. They could literally overlay their graph on top of Cassini's graph and see if the peaks and valleys lined up.
In the verdict, did they line up?
It was a match. For the smaller organic compounds, the lab produced results closely, almost perfectly, matched what Cassini saw in space. The fingerprints aligned.
That is just amazing. So we have the ingredients from Cassini, we have the process that simulates the moon's orbit, and we have a result that matches Cassini's data.
And the implication of that is profound. First, it confirms that Enceladus' ocean is likely to be very chemically rich. But more importantly, it proves that the moon is actively capable of producing these building blocks right now. We don't need to rely on the idea that a lucky comet hit it 4 billion years ago and just happened to deposit some glycine. The moon can make its own. It's a factory, not just a warehouse.
That really shifts the probability dial, doesn't it? If the factory is running T147, the chance of finding something more than just the basic chemicals has to go up.
It certainly does. It transforms Enceladus from a static container of interesting chemicals into a dynamic environment that is constantly synthesizing the prerequisites for biology. It tells us that the conditions we think are necessary for the origin of life might not have been a one-time event on Earth. They might be happening continuously right now under the ice of Saturn's moon.
Okay. Now, before we all start packing our bags for a Saturn vacation, we have to look at the other side of the coin. We need to maintain our scientific skepticism. Because it wasn't a perfect match across the board, was it?
No, it wasn't. And honestly, science is often most interesting where the matches fail. That's where you learn something new. While they reproduce the smaller compounds beautifully, the appetizers, if you will, Cassini also saw hints of some larger, heavier organic molecules that this lab experiment could not reproduce.
So the lab made the appetizers, but Cassini saw a main course that the lab couldn't cook.
That's a good way to put it, yes. There are discrepancies in what we call the high mass region of the spectrum, and Craddock and his team are very honest about this in the paper. They don't try to hide it or explain it away. They highlight it as the next big question.
So what's the theory? Why is the real moon better at this than our lab in a bottle?
There are two main possibilities, and they aren't mutually exclusive. Possibility A is that our oven isn't quite right. The paper suggests that there might be hotter, catalyzed reactions happening deep in the moon that the lab setup wasn't powerful enough to simulate.
Catalyzed. What does that mean in this context?
A catalyst is something that speeds up a chemical reaction without being consumed by it. On Earth, minerals in the rocks of hydrothermal vents act as powerful catalysts. Maybe there are specific metals or minerals at the bottom of Enceladus's ocean iron, nickel, sulfur compounds that are helping these smaller molecules link together into those bigger chains. The lab experiment was done in, a clean, sterile reactor made of glass and steel. We might be missing the seasoning from the rocky core.
So the oven on the real moon might be hotter, or it might have better non-stick cookware, so to speak.
Exactly. But then there is possibility B. And this brings us right back to the original debate we started with. It is entirely possible that some of that material is ancient.
So it could be a mix. It doesn't have to be all one or all the other.
Right. The plumes might be a cocktail. You have the fresh chemistry, the stuff the lab successfully made, the glycine, the aldehydes, the smaller compounds. That's the stuff being cooked today. But that might be mixed in with old primordial dust that Enceladus inherited when it first formed, which contains those heavy, complex organic sludges that can take billions of years to accumulate in space.
So the moon is baking fresh bread, but it's also kicking up some 4-billion-year-old dust from the floor at the same time.
A vivid image, but yes, that's the idea. And this really highlights the complexity of origins. It is very, very difficult to constrain the exact source of all these organics without actually being there with better instruments. The lab brings us incredibly close. It proves the capability of the moon, but it's not a perfect replica of a world that has been evolving for eons.
It seems like we're at a point where we've learned as much as we possibly can from here on Earth. We've looked at the photos, we've analyzed the old data, we've run the simulations, which leads us to the final leg of our journey today, the bridge to the future. Because the reality is, we aren't going back anytime soon, are we?
That is the somber, frustrating reality of planetary science. Space missions take decades to plan, fund, build, and execute. As of right now, there are no dedicated missions to Enceladus or Saturn's rings that are approved and in the works, ready to launch. We are in a waiting period. Even if we approved a mission today, it would take years to build and then 7 or 8 years just to travel there.
That is so frustrating. We have this smoking gun, or this smoking steam vent, I guess, and we can't go check it out.
It is frustrating, but this is exactly why this study is so valuable. As Max Craddock put it in the paper, laboratory studies like this provide a critical bridge between past measurements from Cassini and future exploration.
It keeps the science alive and moving forward while the rockets are all grounded.
It does more than that. It actively progresses the science. We don't just sit on our hands and wait for a rocket. We bring the destination into the lab. By refining these experiments, by testing different catalysts, different pressures, different temperatures, we are essentially doing reconnaissance for the future. We're mapping out the possibilities.
So when we do eventually go back, maybe in the 2030s or 2040s, we'll know exactly what to look for.
Precisely. This study sharpens how we should interpret data from any future mission. Before this work, if we went back and found glycine, we might have argued about its origin for 20 years.
Is it contamination from the spacecraft? Is it ancient cometary material?
Exactly, all those debates. Now we know. If we see glycine in a certain ratio with other molecules, it could very well be from this active freeze-thaw cycle. It gives us a specific fingerprint to search for.
So it tells the engineers what kinds of instruments to build.
That's the bottom line. Craddock points out that future missions need instruments specifically capable of verifying amino acids with high precision and high confidence. We need a better nose than Cassini had. A much better one.
And we need a nose that can distinguish between ongoing internal chemistry and ancient material. We need to be able to tell the difference between the smell of fresh bread and the smell of old floor dust.
And that requires technology that is tuned to the specific chemical signatures this study has identified. You can't just send a generic off-the-shelf sensor. You need a sensor that is looking for the specific ratios of nitrogen to carbon, for instance, that are produced in these freeze-thaw cycles versus what you'd find in a meteorite.
So this paper isn't just a report on a cool experiment. It's a requirements document. It's a roadmap for the engineers who will build the next generation of deep space probes.
Yes. It's a perfect way to put it. It tells them, here is the target, here is the fingerprint. Build a machine that can hit this bullseye from 1 billion kilometers away.
It's amazing to think about the progression, isn't it? We started with these blurry images of a moon from the Voyager probes in the 80s, a white dot. Then Cassini flew through its breath in the 2000s and gave us a chemical list.
Yeah.
And now, in 2026, we are simulating its heartbeat in a pressure chamber in Tokyo.
It's a testament to human curiosity and ingenuity. We found a single, tantalizing puzzle piece in 2004, and 22 years later, we are still turning it over, looking at it under different lights, trying to understand the incredible picture it belongs to.
So let's wrap this up. We've gone from the discovery of the plumes to the recreation of the ocean in a lab. We now have strong evidence, stronger than ever before, that Enceladus is actively, right now, cooking up the ingredients for life.
And it completely challenges our traditional view of the solar system. We used to look for life only in the Goldilocks zone, that perfect narrow band of distance from a star where liquid water can exist on the surface, like Earth. But Enceladus teaches us that with enough gravity from a giant planet and the right basic chemistry, you can have a warm, wet, organic-rich chemical factory in the deep, dark cold, far from the sun.
It's not a dead rock. It's active. It's doing something.
It is. And the fact that we can replicate the basic process in a lab means the physics and chemistry are universal. It's not magic, it's mechanics. And if it happens there and it happens here on Earth, it can probably happen in countless other places.
Here's a final thought to leave you with. We talked about how a simple cycle of heating and freezing in a laboratory running for just a few cycles, probably over a few weeks, was able to create amino acids like glycine.
Right. A blink of an eye in cosmic time, a geological instant.
Enceladus has been doing this cycle for millions of years.
Maybe billions, ever since its orbit stabilized.
Billions of years of this constant rhythmic cooking. If a few weeks in a lab in Tokyo gets you to amino acids, what does 1 billion years in a warm, dark, nutrient-rich ocean get you? What else might have formed down there that we haven't even thought to look for yet?
That is the question. And until we go back, the lab is the only place we can even begin to try and answer it.
The universe is definitely busier than it looks. Thanks for exploring the oceans of Saturn with us. Stay curious about the worlds beneath the ice.
Goodbye, everyone.